Welcome to our virtual Earth lecture series. Just in case you're bored with life and things don't seem to be going wrong in the world, I thought I'd give you a session today that was all about volcanic eruptions and things going badly wrong, maybe in your neighborhood. We are broadcasting to people all over the world, and so looking forward to seeing what you might have to contribute in Q&A later on. The idea of this series is to bring leading edge science and policy experts to you wherever you are. Of course, the global pandemic has raised the stakes of our contributions to the planet and has actually provided a vivid test of our ability to communicate, think, and act as a planet, as an organization of people who might want to coordinate our activities and think carefully. And of course, there are similar issues facing us in the longer term. If you like, climate change is a longer term pandemic we've got to think about. And so far, of course, I think it's been pretty clear that we're not that great at actually taking action, and everybody takes different action depending on where they are. So it's really important that we communicate in ways better than ever before. And part of what we want to do with the Earth Institute and these series is to actually communicate to you and hear from you about issues that we think are of global importance going forward, and major challenges, of course, that face humanity and the planet. So just a little bit of perspective on who we are. Columbia University's Earth Institute's been around for over 20 years. And it's the biggest organization of its kind, and it's particularly large because we have the Lamont Doherty Earth Observatory, which is a major facility for geosciences research, the biggest of its kind in any university in the world. And it's been incredibly effective over the years at taking us forward in science, in particular with the first complete map of the ocean floor, a lot of the work around plate tectonics that was foundational to the revolution of the earth sciences, and then massive work that was done in terms of understanding how the oceans work in particular, and an increasing focus on the issues of climate change going forward. But it's also been cutting edge in terms of its technology and development. We put a seismology device, seismometer on the moon so that we could actually do some of the earliest measurements that were taking place there on how the moon works many years ago. So it's a place of innovation, creative thinking, and in particular thinking about how the Earth works. And that's particularly important for today, because today we're going to be talking with two scientists from the Lamont Doherty Earth Observatory. And the talk is going to be, or the subject of today's discussion is the volcano alarm, anticipating eruptions, and why this can actually, new science is actually giving us clues as to how volcanoes work or may be working, and are there ways in which we can figure out and forecast what might be happening. We have two brilliant experts with us today. Terry Plank is the Arthur D. Stork Memorial Professor in the Department of Earth and Environmental Sciences at Columbia University. She is a geochemist who studies magmas associated with the plate tectonic cycle and is known for her studies of subduction zones, the inputs on the ocean floor, the temperatures attained beneath volcanoes, the melting processes in the mantle, and the gas content of magmas before they erupt. And of course, we'll be hearing a bit about that today. She's a member of the National Academy of Sciences. She was one of the authors of the Academy's recent report called ERUPT, which highlights the incredible opportunities in volcano science. She's also highly traveled in her research. She's worked on explosive volcanoes in Nicaragua, Italy, and Alaska, for example. Einat is an associate research professor at Lamont, where she started as a postdoctoral fellow in 2009. Einat investigates the fluid mechanics and physical processes controlling volcanic eruptions, illuminating how the complex properties of magma and lava, along with variable eruption conditions, play a role on the outcome of eruptions. In addition to publishing in scientific journals, Einat has written for popular science blogs and appeared in radio interviews. In fact, Einat wrote a blog for CNN about her on-the-ground work during the Kilauea eruption. It was among the network's most read articles for the year 2018. So I'm going to kick off by asking Terry and Einat if they will give us a bit of background on themselves and their research. So Einat, over to you.
Oh, thank you, Alex. It's wonderful to be here tonight with you guys. I'm actually speaking with you today from Israel, which is where I grew up, and I'm here visiting in quarantine at the moment. And it's also where the last volcanic eruption was more than 100,000 years ago. So it's not exactly a super active volcanic area, but this is where I fell in love with rocks and with physics. And it's this passion throughout my life that led me to study eventually what I study now, which is volcanic eruptions. And like you said, what I specifically am interested in is how the physical properties of the rocks and the magma affect how eruptions evolve and happen. I got my degrees in Tel Aviv University and at MIT, and then I came to Lamont and Columbia a little over a decade ago.
Great. And Terry, tell us about you. Terry, you need to unmute. Sorry.
Yep. Hi, everybody. Thanks, Alex. And it's wonderful to be here today. I'm actually speaking to you from my kitchen in Nyack, New York. I literally grew up surrounded by geology. I was born in a rock quarry in Wilmington, Delaware, in a culture that was rich in science. Almost everybody worked for the DuPont company, so nobody thought it was weird that there was a girl who liked to work on rocks and science. I went to Dartmouth College because it had a great outdoor earth science program. After that, I did a postdoc at Cornell University and had teaching gigs at the University of Kansas, Boston University, before returning back to Columbia, where I actually had gotten my PhD as well. I'm incredibly lucky to both teach some of the smartest students in the world, and also to work on the famous Lamont campus where flocks of turkeys and earth scientists roam the woods. I can't really speak for the turkeys, but it's an amazing place with incredible breadth of expertise across earth science, from the climate system to earthquakes to volcanoes.
Wow, that's great. You really shouldn't call your colleagues turkeys though. So can I ask you both, what led you to pursue scientific research and specifically volcanology? What got you into this, Einat?
As a child growing up, I was always outside, hopping on the rocks, jumping, hiking, and camping, and collecting fossils and looking at, the layers and pointing out all of the interesting things. But I also really enjoyed math and physics, and I was into robotics and programming and things like that. Then in college, I discovered there was a major called geophysics, and I was like, this is what I was looking for my whole life. And it was great, so I gave it a try, and that worked out really well. After college, I did try for a few years to work in tech, in programming. It was, just before 2000, everybody was doing that. But I pretty quickly realized I really needed that connection to nature and also the independence that science can give me to follow what interests me. So I went to graduate school and started looking at how the earth works, the physics of the earth, and then kind of focusing into volcanoes, so that, because I felt I needed to have a more concrete kind of connection to people's lives also, not just the earth.
Terry?
So as you know, major chunks of the theory of plate tectonics were really developed at Lamont, and so that's why I was drawn there as a graduate student. There had already been a lot of work on what made the plates move and how they created earthquakes, but there hadn't been as much work really on why they generated magma and volcanoes, and so that's what I was really drawn to. Also, as a graduate student, I got to go out to sea. I, in fact, drilled the seafloor that was entering the Marianas Trench, which isn't just the deepest part of the ocean, but it's where the oldest ocean crust is sinking into the earth, taking water with it. And I traced chemically that water back out to volcanoes in the Marianas Islands. So for me, volcanoes have always been kind of a portal into conveying the information from the deep earth, much like Jules Verne's journey to the center of the earth. And really early in my career, it was kind of a nuisance that the volcanoes erupted. It made it difficult to study them. But as my career has gone on, I realized that the work that I've been doing, understanding what happens in the deep earth, is important for eruptions, specifically, again, the water that makes gases and CO2 and sulfur. These both drive the explosive eruptions and are the culprits for really catastrophic climate events of the last centuries, like at Krakatoa and Tambora. My most recent research has really shown how the textbooks are wrong, that it's not kind of how much gas that fuels the eruption, but like anyone who's been handed a seltzer bottle or a soda bottle that's been shaken vigorously, you know it's not how much gas it's in there, it's how fast you open the cap. And so we've learned a lot that it's the rate, it's the timing of events before eruption that drive explosivity. And this is what we're working on now, how fast the cap opens at volcanoes.
So one thing, that was amazing, but one of the things that you said, sort of suddenly I thought, wow, that sounds great, of course, is that you trace water that's being taken down into the Earth's mantle, which is down to about 100 kilometers, and then comes back up in volcanoes. And to most people, that just must be mind-blowing that we can actually do that and actually trace water molecules and actually see them. So at some level, I guess volcanology and what you do with geochemistry and petrology is kind of forensic science, isn't it? You're trying to figure out how the Earth works from what comes out of the top. Can you tell us a bit more about that? How does the looking at the volcano after eruption really inform how the volcano work and the volcanic systems work?
It's a good way to put it, as a forensic science. In part, I work this way because it's pretty dangerous to go to volcanoes while they're erupting. So it's certainly safer to go to the crime scene after the event. But more to the point, only after the eruption can we collect the material that was actually witness to what was going under the ground before the eruption. My focus is really on the most violent explosive eruptions. And these actually don't produce lava. Einat's going to talk to you about lava, but the eruptions I work on produce big plume clouds that I'm sure you've seen. They're big roiling clouds of ash. They may look like smoke and ash from a fire, but you know, they're not. They're actually frozen magma. They're bits of glass. So they're hazardous to breathe. They bring down aircraft. They cause aircraft to fail, this ash. But we use them because they're incredibly valuable tools. The ash is the magma itself, and its chemical composition, much like a genetic code, records in it the depth that the magma came from, how hot it was, how the gases escaped. And these are the vital clues that we need to know about how a volcano prepares to erupt. So we try to go as soon after an eruption as possible, before all the ash blows away. We collect gallons of the material. We bring it back to our labs at Lamont. We sift through them for tiny little crystals, the width of a human hair, and then we zap them with lasers, electron, and ion beams to read this genetic information of what was happening before the eruption.
Wow, so that's a great way of putting it. So another aspect of your work actually involves instrumentation, right? So, and sort of monitoring of volcanoes. Can you tell us a bit about that as well?
Right, so I'm sure you can imagine the forensic approach that I just talked about. It's essential to knowing what was going on under the ground before the eruption, but it really can only be used in a hindcast, that is after the fact. If we want to actually anticipate eruptions, that is to forecast them, we need to measure the warning signs that occur before eruptions. And fortunately, unlike earthquakes, which don't do much, volcanoes do a lot before they erupt. They produce microseismicity, little earthquakes as the magma is moving under the ground. The ground literally swells because the magma exerts pressure as it tries to rise and erupt, and gases escape. And we've only learned about all these phenomena in the past few decades as we've deployed arrays of seismometers to measure the earthquakes, GPS receivers to really measure the moving ground, and placing gas sensors near craters to measure the flux of CO2 and sulfur. The problem is, even though we can measure all these things, most volcanoes actually aren't instrumented in this way. And those that are, the data are not broadcast in real time yet. Almost no eruptions have been forecast. Just a few weeks ago, a volcano erupted in Alaska. It's called Cleveland, and it erupted into airspace. During non-COVID times, 80,000 people a day fly over Alaska volcanoes, 80,000 people a day. So this is certainly relevant to a lot of aircraft. There is one seismometer on Cleveland right now, and it has communication normally to Anchorage, but that communication hub is down. So we actually knew nothing about this eruption before it happened. It's pretty remote and windy out there. And the next time we'll be able to learn about this volcano will be next summer when we get back to download the data from the seismometer. So this is incredibly frustrating. You could imagine it's like trying to forecast a hurricane. You know there's all these things you should be measuring. You should be measuring the sea surface temperature and how fast the wind is blowing. But let's say this was before we had real-time data from satellites or ocean buoys. This is where we are with volcano forecasting. If we can just get the real-time data and have sensors that are broadcasting in real time, we'd really have a breakthrough in anticipating eruptions.
That's fantastic. Interesting to hear about that. So, I mean, of course, the kinds of volcanoes you're talking about are really violent and explosive. But Einat, you've been working on much more passive things. So, I mean, you would never recommend going anywhere near a volcanic eruption like the ones that Terry has been talking about. But in your case, you were working on Hawaii, where you can actually get up close, which is sort of because there's less volatiles involved, I guess. So, well, you'll tell me the details. But you and your team were among those on the scene at Kilauea in 2018. What was it like to be there as this amazing, mighty volcano erupted?
Right. So, yes, like you guys mentioned, I studied which is less violent and doesn't have this very spectacular plume, but then once it erupts, it stays on the ground and it can devastate a community and its infrastructure, cover houses, cover roads, and the rocks just stay there for the longest time. And it also has a forensic aspect to it because lava flows are what's left behind an eruption and can tell us the eruption conditions for a really long time, even billions of years afterwards, like we see on other planets as well as here. So when the eruption started in Kilauea in 2018, we were really looking closely to see what was going to happen. We weren't sure if we wanted to go, didn't want to go, how long it's going to be. Is it going to be kind of a puny one-off fissure that opens and maybe not? So we're monitoring everything really closely. And then we said, okay, we just have to be there because the kind of research that we do, we need to see the lava as it's moving to really understand how it moves and what it's like. So we just booked airplane tickets and went there, me and my two postdocs. And just when we got there, it was a scene from another world. It was just unbelievable. Just driving around at night in the empty roads because everybody has been evacuated, and the National Guard at the posts monitoring who goes in and out. Everybody gets their gas sensor to make sure that you're still in a safe limit, and a gas mask to make sure that if you are exposed to high gas, you got to get out of there safely. And the sky was glowing. It was reflecting the magma as it was erupting from the vents. It was really from kind of like a sci-fi movie. And it was very, very quiet. And if you imagine Hawaii has very thick vegetation, you could drive on the road, know that there's an eruption and that there's a lava flow 500 meters away from you, and you can see nothing unless you see the glow in the sky. It was crazy. And that's really where things proved very useful for us, that we joined with a team at the University of Hilo that has experience with using drones to monitor volcanic eruptions. And we also brought our own drones, and it was highly advantageous because we were able to provide night vision capabilities with thermal cameras. So we're able to operate at night. The helicopters and the police and fire department couldn't. So we could launch our drones at night and provide real-time information to, for example, the road crew that was trying to tell people to go or not to go. And our drones up in the sky were providing information. Is the lava coming our way or is it not? We got called one night to the geothermal plant because the lava was moving their way. They wanted to see how fast it was moving, and it was at night. We launched the drones and collected the data, that kind of first information. So it was just incredible experience to be part of the response, and not, usually I sit in my lab and on the computer and I think about the theory and the physics of everything, but this experience to really be on the ground and see how it's going on was priceless. It was also really and humbling and awe-inspiring that we shared an Airbnb with a family that was evacuated from Leilani Estate. That's the community where the fissures, the vents opened. So just really being close to the people that are really affected by it was quite something.
Yeah, that human experience must be amazing too.
Yeah.
So, great that you did this, and must have been an amazing experience. How did your work actually help drive forward our understanding of volcanoes, though? Was it
Right.
useful? Oh.
Yeah, it's been extremely useful. So I study how lava and magma are the same, just outside and inside the volcano, how it moves and how it deforms under different conditions, depending on how much crystals you have in it, how hot it is, how much bubbles you have in it, and to really see that and be able to get better models that would help us predict where a lava would go or how fast magma would go up inside a volcano. To make these models better, we have to have these observations, and it's very tricky to collect them. But this eruption, because it was so long and because it was so well studied on the ground with the incredible response by the USGS and academics, now we have all this information that we can put into models. And going forward, we'll be able to say not just what area of the volcano is going to be covered, but how fast it will get there, how quickly it can inflate and deflate, how thick it might get, so that people can plan their response, know when to evacuate, what kind of structures are in danger, much more detail.
Fantastic. So, Terry, you're embarking on a breakthrough project called, maybe other people should say it's a breakthrough project, but it's a breakthrough project called AVERT. Do you want to tell us why it's a breakthrough and what you will be doing and what you hope the outcome will be? Terry? Terry, you've frozen. Right, we've got a problem here with Terry and her line. Well, okay. So maybe the best thing is, Annette, you're involved in this project as well, aren't you? So why don't we just, why don't you give us a quick overview of how it's going, and and then also talk to us about what's actually planned for how it's going to go on.
Yeah, no, happy to. Terry and I have initiated this project about a year ago, and it's a 5-year, $2.4 million funded by the Gordon and Betty Moore Foundation. It's a group of 8 of us at Lamont together with the Alaska Volcano Observatory, as well as international partners. And the acronym AVERT, it stands for Anticipating Volcanic Eruptions in Real Time. And the idea is to really bridge the gap, like Terry was mentioning about Cleveland, between collecting the data, monitoring the volcano, and making the data available in real time and openly to scientists to use. We are targeting 2 volcanoes up in Alaska. They're called Cleveland and Okmok, and we're treating it as a test bed to really try different configurations of networks and different combinations of instruments. We're going to use seismometers to measure the earthquakes, GPS, gas sensors, a much heavier use of cameras, gas cameras, thermal cameras, infrared, as well as regular webcams to really see what's going on in these volcanoes. We chose these 2 because they are very active, but in a different way. Cleveland erupts almost every year. And is releasing gases almost all the time. So there's always something going on with it, but it keeps its shape. Okmok is a little bit the opposite. It erupts, the last eruptions was in 2008, but right now it's inflating. So we're suspecting that we're going to be able to see some of these precursors before its next eruption if we stay there for a long enough time. So we want to establish a baseline, identify the precursors, and really try and give this as an example for what happens when you look closely with different parameters, different instruments, and open the data right away in real time, how much more we can learn than what is traditionally being done on volcanoes.
So this is a 5-year project, right? So, so I guess you need. Sorry, Terry, we just covered a lot of your stuff on the.
That's okay. I dropped out. I'm glad I got back.
So this was a plan for 5 years, right? So why 5 years? Why do you need 5 years? And what will you hope to achieve over that period of time?
Right, like I said, Okmok, for example, takes almost a decade, sometimes more, between eruptions. And
so you have to have that period.
We have to have some kind of a window to hope to catch one. We also, for Cleveland also, you want to have more kind of data points in your statistics. If it has 5 eruptions in that window of 5 years, that'll be great, because in terms of science, it'll give us a lot more information rather than looking at one eruption, to look at what's common and what's different between those different events. And it will also provide an opportunity for partners to join in, maybe test new kinds of instruments, new methods, and demonstrate capabilities that hopefully this example, this test bed at Cleveland and Okmok and AVERT, will then take us forward to provide an example that can be deployed everywhere around the world.
So can I just ask a stupid question? Why hasn't someone done this before? Because it sounds like Cleveland didn't have any much of an observational base at all, and why don't people just put stuff there to make sure they know what's going on with these volcanoes? Is that a silly question, Terry?
Yeah.
It's not a silly question. It should be done. It's just a matter of money and access. So there's a lot of volcanoes that are difficult to get to and difficult to keep working, and we're trying to build a more robust array so that the communication will actually go via satellite instead of via radio. That hasn't really been possible in the past because there hasn't been enough bandwidth on most satellite connections to transmit full video images and seismometers. So it's really been enabled by technology in the past few years that now we can fairly cheaply transmit a lot of data directly through a satellite connection. So
right.
There's also the angle that people tend to study what they kind of like what's under the lamppost, right? So there's been there's a few lab volcanoes that people have studied for decades. I mean, Etna has been instrumented with every possible instrument. Hawaii has been studied pretty heavily as well. But there's volcanoes that don't erupt every week or every year, or they're not as close to population, so they're more heavily monitored. So that led to a bias. Some of our understanding and models is biased because only few classes and few volcanoes are monitored sufficiently. So if the idea is that if we have this package of instruments and methods and protocols that people follow, then maybe we can canvas the whole world, and that might change what we think, because we look at places we haven't looked before.
That'd be really interesting, quite apart from important and useful, you know. So, normally, you know, the Earth Institute thinks a lot about the issues of sustainability of the planet, and climate change, of course, is up there at the top in terms of the biggest things we're worried about. Is there any link between climate change and volcanoes? Because you're putting gases up there, right? Terry, you got cut out of the conversation. So do you want to come in on that one?
Sure. Indeed, there is a clear connection. The next magnitude 7 eruption will be the next major climate crisis. We know that the eruption of Tambora volcano in Indonesia in 1815 created the year without a summer. It was snowing in New York in June. We'd have snow right now. But this was devastating, of course. It created widespread crop failure. And globally, it was really the worst famine in the 19th century. Almost 100,000 people died globally from Tambora. And Tambora is many times smaller than a super eruption like from Yellowstone, which has happened many times in Earth history. Tambora injected sulfur, so it's the sulfate that's reflective and causes cooling of the Earth's atmosphere and surface. Volcanoes also inject CO2, and that leads to long-term warming. There is no reason why a Tambora-sized eruption couldn't happen in the next decade or the next hundreds of years. Okay, but this is why we need sensor arrays that are listening and anticipating eruptions. Of course, we're also living in this incredible time in history of the global pandemic. And so we're thinking a lot about global events. Volcanic eruptions are going to continue. We can't stop them, but we can learn to read their warning signs and to prepare for the disruptions. Columbia University has, as you know, the National Center for Disaster Preparedness. They've really been a leading voice through the pandemic. Many of us have heard them on a lot of on news outlets. And through the Earth Institute, we're really hoping to build new partnerships between the scientists at Lamont and the experts at Columbia, building a kind of new volcano institute to do both of these kinds of activities. This kind of pan-institute of science and social science doesn't really exist anywhere in the world right now. And we think it's something Columbia is prepared to lead in.
Great. So I've got loads more questions I'd love to ask you, but just let me ask you one key thing about the fact that so many people live quite near to a volcano, millions. So what would you like to say about risk and what we are doing, you know, what humanity is doing to really help protect people going forward? Maybe we can't stop volcanoes, but we can maybe do something around risk and resilience. Einat, do you want to come in on that?
Sure. Yeah, so people live in a lot of places that there's some hazard that is threatening them. There could be a pandemic that's anywhere in the world. It could be tornadoes, could be hurricanes, and in a lot of places it's volcanoes. Volcanoes have a lot of good things about them that draw people to live there. They provide energy, fertile agricultural land, also minerals. But yeah, they present a lot of danger as well. So communities who live near volcanoes, often they're pretty knowledgeable about what's going on in their backyard, but they also need to be really active and make sure that the government agencies have the instruments and the capabilities to monitor and provide adequate information, that they're well funded, that those agencies share the data and the information with experts around the world, and are open about it and not just keeping it to themselves, which sometimes agencies do. And also that those agencies communicate with the public openly. The communities need to kind of expect the agencies or the observatories to do town hall meetings when something's happening and be open about what's going on all the time. For themselves, individuals and organizations need to be self-resilient and have their own plan of what they're going to do. With volcanoes, unlike, for example, an earthquake or a passing hurricane, sometimes an eruption can last a long time, and you don't know how long. This is part of what we're trying to study. How can you tell how long an eruption will be, when it will end, and how? So if an evacuation order has been issued, people need to be prepared that it might not be a week, it might be 3 months, it might be a much more extended period of time, and have a plan. Who goes back to walk the fields, who doesn't, what do you do with all the kids? We've all been in quarantine for 3 months. We didn't exactly have a great plan for how to deal with that. So people who live near active volcanoes should have these plans. And volcanoes have different types of hazards. They can have lavas, they can have pyroclastic flows, they can have ash. So if you live near a volcano, you got to really know it, know what it's capable of doing, what it's done in the past, push for the research about the past events to happen, and the results to be shared. So just acquire all that knowledge.
Wow. Okay. So there's a lot of questions coming in, and so I'll try and sort of collate some of the main things that are coming out, and then at the end, what I'll do is ask each one of you to provide one takeaway message that you'd like to give the audience today. But let's take a look at some of the questions that are coming out. One of the one of the questions that's coming in, as we lose glacial and polar ice, I should say to people, there are so many questions coming in, we've only got a limited amount of time, so we'll make the questions succinct and we'll make the answers succinct, but we probably won't get through everything anyway. As we lose glacial and polar ice, do we expect a shift in the distribution of water and its weight distribution on the planet to result in changes from volcanic activity? I think that's really interesting. Terry, yeah.
This is super cool, and it's a new area of research. There is a connection between sea level and how it affects submarine volcanism, so the weight of the ocean, and then also how ice sheets, due to their pressure, affect volcanoes. Only in the past, say, 20 years did we see the detailed record from Iceland that the volcanism there was definitely modulated by ice sheets. So when there was ice sheets, it suppressed volcanism, and when the ice sheets melt, it released them, and there was extra volcanic activity. We've seen hints of that other places in the world. So there's definitely a concern as we melt ice, especially mountain glacier type ice, or change the balance of sea level, that we will change the frequency of volcanic eruptions. We certainly have in times of Earth past.
Yeah, amazing. So another question coming in, can you get real-time pre-eruption information in the age of satellite and internet communications? So I would have thought this must be a yes, but do you want to tell us a bit about that, Einat?
Yeah, the technology is there. We can. The problem is you need to have the instruments to collect the data, and many volcanoes don't even have those to collect the seismic signals and the GPS and all that. Then you have to connect it to a satellite antenna to send the information up. Then there's a question of bandwidth. You may be able to send some of the data, but until very recently, it was very limited. You could send a text message every 5 minutes with a number, but you couldn't send, high frequency 100 hertz seismic signal from seismometers. You definitely couldn't send pictures like we want to do, say, with some of our gas or the thermal cameras. So things are just building up now towards enabling us to do it. It's not, rocket science. It's not reinventing something that doesn't exist. It all exists. It's a question of money and putting the instruments on the ground and having enough satellite communication bandwidth.
Okay, that's great. Okay, another question's come in, which is a great one. While the plasticity of lava is different for an explosive volcano than a drive-in volcano, which I think is a brilliant term, which of the two types of lava produced in each, and why does it happen? Why do you actually get these differences between volcanoes that are so striking? Terry, do you want to quickly explain that? So,
Einat's the lava expert, but
okay.
part of it is the stickiness of the magma. So hotter magma is more fluid. Hawaiian magma is very hot. The Yellowstone super eruption magma is very cold and sticky. So there is a stiffness to the magma. But as I said before, for magma that actually has the same runniness, you can have explosive and non-explosive behavior. And that has to do with how the gas gets out again. If the magma races to the surface and brings the gas with it, it will explode violently. If it moves slowly and the gas kind of trickles out, then it will ooze on the ground as a lava. So those are some of the factors that are governing whether you get lava or explosive eruption.
When you say cold and sticky, it's not really cold, is it?
Okay, it's not so cold.
It's like 700 degrees or something.
Yeah, 1400 Fahrenheit. But Hawaii is like twice as hot, 1400 C. Yeah.
Yeah. Okay. Great. Thank you. So somebody's asked about supervolcanoes, talking of Yellowstone. So are there probes that might give us some warning about these? And are there things that can be done to release the pressure less violently than might be expected if a maximal eruption should be building? I know they talked about that with Lake Nyos many years ago in Cameroon, getting the gas out so that it didn't erupt again from that volcanic lake. But what about volcanoes? Is there some way to actually take the pressure off a volcano? And are there probes that might give us some warning that Yellowstone's about to blow? You're shaking your heads, nodding your heads.
Yes, right.
Yeah, so
go ahead, Einat, you can do this one.
I mean, we can monitor these volcanoes. Yellowstone is definitely being monitored closely. There is a Yellowstone Volcano Observatory by the USGS, and they have a lot of instruments, and they monitor it closely, which is why they can tell us that it's not likely to erupt anytime soon. But there's really not much you can do about releasing that pressure. It builds up, and it's a lot of pressure. And you also, even if you could, you don't want to mess with it because you don't know what the result is going to be. Mountain Helen eruption built the pressure inside the volcano, but what really got it going is when the side fell. So you don't know what would happen if you say poke a volcano and open a little hole to release that pressure. You might just be giving it that one push to make it actually go, even if it was physically possible, which is not.
Yeah. So, I mean, in terms of really big eruptions, which we haven't seen, like Yellowstone in recent human history, is there some evidence now from the geological record, of what actually preceded these eruptions that might give us a clue that something like this was going to happen? If it did, it would devastate the United States and actually the world, of course. But if, there must be some clues that we've now figured out in the geological record of what preceded these super eruptions like Long Valley, etc. Terry, do you want to comment on that?
So there's some evidence that they've been triggered by the input of new magma. So that is one of the things that we're studying, is how volcanoes are triggered. So some of the largest eruptions are sitting there kind of sticky, and the new magma comes in and can actually loosen it up and cause it to erupt. I think for Yellowstone, it's so big and super eruptions are so large that in order to mobilize that amount of magma, it has to be largely liquid. And so one of the ways that we're studying Yellowstone closely is with large seismic arrays that are like X-rays looking at the magma under the volcano. Right now, it only appears to be 10% liquid volume. The other 90% is crystals. And so that probably can't move. But when we see the amount of liquid increasing, the amount of magma increasing, that's the concern, I think, that then it would have enough movable magma to erupt.
Great.
Also, if you have that much pressure building up, you'll see signals at the surface in terms of the ground deforming and rocks breaking and creating micro earthquakes. You'll have signs when something like that is building up. It's not just going to catch us by surprise all of a sudden.
Yeah. Right. Okay. So there's another question here. How many active volcanoes are there in the mainland United States and Alaska that could be monitored by AVERT, and how much would that cost? Yeah, Terry.
I'll give it a shot. So I said there's about 40 or 50 historically active volcanoes in Alaska. That's where most of the active volcanoes are. There's actually 3 in a state of unrest right now in Alaska. And then there's Hawaii, and then there's about a dozen or so in the Pacific Northwest, like Mount Rainier, Mount St. Helens, Mount Hood. There is actually a bill that had passed, bipartisan bill, that's called the National Volcano Early Warning System, that's going to the USGS. It's $55 million to build very sparse monitoring on 150 volcanoes in the US that have erupted in the past 10,000 years. So a lot of them aren't particularly active, but we feel we need to have our ear to the ground. So that's going to be building out a very sparse and disperse array. It's why we wanted to jumpstart it with the private funding with AVERT, to build a more dense array that then has this real-time capability and actually brings all the multi-sensors, not just seismometers, but GPS, gas, visible. We're trying to get the price tag for an array per volcano down to a few $100,000. So say $500,000 per volcano. There are about 80 volcanoes in the world right now that are doing something. They're emitting gas or they're swelling. Right now, 80 probably. So it's not thousands. It's like 80 that are doing something that we could be measuring right now. And so putting a $500,000 array on those 80 volcanoes, that's $40 million. This seems like something that could be solved with judicious funding.
Yeah, I mean, one of the questions, follow-on questions, was how close are we to having an early warning system? You're saying we could do it tomorrow pretty much if we just spent the money. Is that fair? Is that pretty much, we actually know how to do this?
Well, that's partly yes. I mean, the NVIEWS bill has been passed but not appropriated. So that is money that has not arrived yet, and that will certainly help. I do think a lot of it is funding and instrumentation. But there is an important community aspect to this, that saving lives on volcanoes requires the things that Einat talked about, which is good communication and national observatories. Every volcano is in a different country, or the volcanoes in different countries. Each one has its own observatory. It's a national mission to monitor and safeguard their citizens. We need to coordinate all that better and have all that data shared.
Yeah.
Right. And also you can have all the data in the wall, but if you don't know, you don't have the theory and the physical models to interpret it and put it all together. And what do you do when the gas tells you one thing and the seismic tells you something else? Then we still have that leap to do in theory and in models, even once we have the data. So there's still a few steps to go.
So somebody's asked why you chose Alaska, because there are plenty more people living in around tropical volcanoes. Why would you go? I mean, Alaska doesn't. I don't want to be rude to Alaska, but would it be more worthwhile to do it somewhere else where there are more people living? Yeah.
I mean, we chose Alaska because the volcanoes there are doing something. We don't really want to put an array somewhere
where nothing's happening.
Where nothing's happening. So, like I said, there's 3 volcanoes that are in a state of unrest, or 2 that have erupted this year from Alaska. Hawaii's not erupting, nothing's erupting in the Cascades. So it's a matter of, we want to measure things. The volcanoes in Alaska are doing something. They're also a good natural laboratory, right? They're sitting there ready to be studied remotely. But it's also not true that they don't hurt anybody. As I said, there's 80,000 people a day that normally fly over Alaska airspace.
Yeah.
One airplane costs several $100 million, not to mention lives lost, potentially, if the airplane fell out of the sky. So it's actually an enormous hazard in the US of having 40 or so active volcanoes, where almost every flight route from North America to Asia takes you over Alaska volcano airspace.
Yeah, yeah.
We also wanted to go to a place where we can hit the ground running in terms of having the kind of backbone capabilities and the data sharing protocols and having an established connection with the scientists on the ground. We could go, and we have proposals to go to Central America. It just orders of magnitude more difficult to convince a foreign government to have a monitoring network that is real-time open, for example. So to show the importance of all these features, we wanted to go to a place that was already established in some sense.
Okay, so we're gonna have to wrap this up in a minute. I want to ask you what your takeaway messages are going to be. There's one last question here. What sources do you recommend to a college junior studying earth sciences now? Which I thought was such a good way to finish off. So, or maybe, what would you say to somebody who's studying earth sciences now, who would like to find out more about this particular area? Terry, do you want to?
Sure. Take a lot of courses in earth science, in volcanology. There is a really great resource, which is this National Academy report called ERUPT. It really is very readable. It has great photos and images, and it really is a state of the art of volcano science. It's free. You can download it from the National Academy website. But get involved in research.
Sounds great.
Yeah.
Okay, so I'm afraid, even though there's lots more questions coming in, we're going to have to wrap it up in a minute. I just wanted to quickly ask each of you what's one takeaway message you would like to have for each of the individuals who are listening in today. What would you like them to really grasp? So, Einat, why don't we start with you?
Yeah, I hope that I convinced at least some people of what I believe, that volcanoes sure are dangerous, but they're also such a fascinating target to study. And what's really beautiful is that there is something for everybody. It's a truly interdisciplinary target. There's if you want to study, if you're interested in physics, chemistry, computers, math, that's an obvious place that you can use those skills. But also if you're interested in history, sociology, communication, archaeology, it's such a target that everybody should be working together and need to be working together, that there's a place for everyone, and we need everyone to be involved and to really be effective. So I hope that message goes through.
That's great. Terry?
Right, my message is a mix of a human message and a practical one. So this has been such a difficult year. It's even hard for me to remember what January was like, so much has happened. But in January, Taal volcano in the Philippines started erupting and led to the evacuation of 300,000 people for months. So we're all tired of sheltering in place, but imagine actually being evacuated to a shelter for months. The volcano actually never delivered the size of eruption that actually warranted this response. So we really need these real-time open data streams. There were no open data from the Philippines for this event in order to forecast lives and also not have these unnecessary disruptions. And so I'll push the math again. There's 80 active volcanoes, $500,000 per volcano. We could actually solve this problem for tens of millions of dollars, a fraction of an airplane. It's frustrating to me, and it's a difficult thing to fund through the National Science Foundation. Our normal funding channels don't work this way, and so I'd love for people idea of how we can jumpstart this so we can transform volcano science and forecasting. Thanks.
Well, that's been great. Thank you very much indeed. So we need to wrap this up, but I want to thank everybody for their contributions. I just want to say that I thought Einat and Terry were fantastic. They're brilliant scientists. It's great to be at a place like Columbia University where we have so much going on in terms of geosciences, focus on the planet, and also how the geosciences interface with people's lives and what we need to be thinking about going forward as we think about sustainability. So it's great, not just because we've got a lot going on, but we've got great people here. So look forward to staying in touch with you in the future as we do more of these events. A lot of what we think about here is climate change, and because it's we think about pandemics as massive emergencies and volcanic eruptions, massive emergencies, but in the background there's this growing crisis with the planet that we need to think about, which is to do with human-induced effects that are quite remarkable, that these little people have actually increase the surface temperature of the Earth by a whole degree centigrade. And this is just remarkable, and it's actually a sign of how heavily influenced the planet is by humans. And we need to do something about that if we want to keep the planet as a safe and habitable environment that's sustainable for younger generations in particular going forward. And particularly when we think about who's going to be most impacted, it's going to be not just future generations, but people who are already severely disadvantaged in terms of their status and their environments in which they're living. So we urge you to engage with us more as we talk about sustainability and as we discuss solutions and how we're going to take this forward. One of the things we're looking at Columbia, which is deeply engaged in this whole issue, from the president of the university, Lee Bollinger, on down, is the idea of building a climate school, which will be the first of its kind. It'll be a very striking structure, but it harnesses the power of Columbia in this area to really deliver what we believe could be informed solutions in partnership with people around the world. So we're looking forward to talking with you more about that going forward, and look forward to more presentations about geosciences, society, and how the Earth and humans can interact more positively going forward. So thank you very much indeed, all of you, for listening, and look forward to further discussions in the future. In the meantime, just a quick round of applause to Terry and Einat for fantastic presentations. Thanks a lot. Stay safe. Bye-bye.
Bye.